Right, welcome back to the chapter 13, gas mixtures. As we discussed in previous class that in this chapter we'll discuss non-reacting gas mixtures. This is lecture number 13. Let's continue. In previous class, we discussed an example that was related when the two gases they are at different temperature, different pressure, and they are mixed together. And after mixing, what is the new mixer temperature, new mixer pressure, and the composition of the mixture, right? But in this example, let's say we already have a mixture of 2 kilomole of nitrogen, 6 kilomole of CO2, and the mixture is available at 300 degrees C and 15 megapascal pressure. What will be the volume of the mixture now? And calculate the volume of the mixture mean volume of the tank based on an ideal gas equation of state, based on the K's rule, and based on the Avogadro's law. So use three different techniques to calculate the volume of the tank. So let's start with the first one, the fundamental one, the volume of the mixture using an ideal gas. I mean, consider mixture as an ideal gas. So we know that the ideal gas equation is PM Vm is equal to Nm Ru Tm. So in this equation, we have only one unknown, which is the volume of the mixture. So volume of the mixture is equal to number of mole of the mixture, universal gas constant, temperature of the mixture, and pressure of the mixture. We know how to calculate the number of mole of the mixture by sum up all the number of moles. So we have 6 plus 2, 8 kilomole of the mixture, and the value of the Ru is equal to 8.31, and the temperature for the mixture is given to be 300 Kelvin, and the in terms of kilopascal, the pressure will be equal to 1500 kilopascal. If you put all the value, then the value of the volume of the mixture will be equal to 1.33 cubic meter, right? So this volume is based on the ideal gas. I mean, you consider the mixture as an ideal gas, right? Now part B says calculate the same volume of the tank, but now use K's rule. Now K's rule is used when we want to predict the volume of the gases, I mean pressure of the gases or temperature of the gas mixture, real gas behavior. So in K's rule, we know that PV, PM, Vm is equal to Zm, Nm, Ru, Tm. So whenever we consider the real gas behavior, we have to consider the compressibility factor. Since this we are considering PM mean for the mixture, so Zm, I mean the compressibility factor for the mixture. So how to calculate Zm, right? Based on the K's rule, right? How to calculate Zm based on the K's rule. So that's the point here, that how can we calculate the compressibility factor using K's rule. Up till now, you have calculated the value of the compressibility factor for a single component, like let's say for the nitrogen. I mean the compressibility factor for the nitrogen, we know that if we know the critical temperature of the nitrogen, we can divide the given temperature with the critical temperature and we can get the reduced temperature. Similarly, we can divide the given pressure with the given critical pressure of the nitrogen, then we can get the reduced pressure. So if we know the reduced temperature and the reduced pressure, then we can calculate the compressibility factor. But now in this example, we have the mixture of the two gases. So how to calculate that? So as we discussed in the theory, and from here Vm is equal to Zm times the remaining factor. So from this equation you can see, I mean the same value as we calculated from the ideal gas. So Zm times the volume of the ideal gas. So the volume of a real gas mixture is equal to the volume of the ideal gas times the compressibility factor for the mixture. So this value we already know. That's the volume of the ideal gas. Now the question is how to calculate this. Now K's rule says that you can calculate the value of the compressibility factor for the mixture by considering mixture as a pseudo pure substance. So what is the meaning of that? In that case, it says that calculate the critical temperature of the mixture separately and critical pressure of the mixture separately. The critical temperature of the mixture is equal to sum of the Vi times the critical temperature of the individual component. So it depends on how much component are available in a mixture. Since in this example we have two nitrogen and carbon dioxide. So first of all, YC Y nitrogen T critical nitrogen plus Y carbon dioxide T critical carbon dioxide. So that means we need to know the mole fraction as well as the critical temperature of both the gases. This we can read from the property table of the CO2 and property table of the nitrogen. Similarly, for the critical pressure of the mixture, we can use the same formula, sum of Yi times P critical I. So depend on the number of components. Since we have two components, so Y nitrogen P critical nitrogen plus Y CO2 P critical CO2. So that means we need first of all the individual critical temperature of each gases and individual critical pressure of individual gases, that we can read from the property table. What about the mole fraction? So how much number of moles are there? If we add up that, 2 plus 6, 8 kilo number of moles. So what will be the mole fraction of the nitrogen? Number of moles of nitrogen divided by total number of moles. Similarly, mole fraction of the CO2 is the number of moles of the CO2 divided by total number of moles. So we have 0.25 for the nitrogen and 0.75 for the carbon dioxide. So now if we put all the values here, let's say in this equation, right? So we have the mole fraction for the nitrogen, which is 0.25, and the critical temperature from the property table, which is 126.2 Kelvin, plus the mole fraction of the CO2 times the critical temperature of the CO2. So this is the critical temperature of the mixture now. So similarly, we can get the critical pressure of the mixture, right? If we put all the values, I mean in this equation, then we'll get the critical pressure of the mixture, right? So now once we have critical temperature of the mixture, critical pressure of the mixture, now we can calculate the reduced temperature and the reduced pressure for the mixture, right? So the reduced temperature is the reduced temperature for the mixture, given temperature of the mixer divided by critical temperature of the mixer. So we'll have the reduced temperature for the mixer. Similarly, reduced pressure for the mixer is the given mixture pressure divided by critical pressure of the mixer. So we have the reduced temperature. So once we have reduced temperature and reduced pressure from the, we know in chapter 3 of the thermodynamics 1, you know how to read the compressibility factor from figure A 15b, which is given at the appendix of the book. So from that you will read the value of the Zm to be 0.49. So now we can calculate the volume, real gas volume. I mean that's Vm, which was equal to Zm times the ideal gas. That means Zm value basically give you the a factor that how much percentage of the ideal volume is basically the volume of the real gas. So that Cm value is a 0.49 times the volume of the an ideal gas. So Zm is basically 0.49 times 1.33, which is 0.652 cubic meter. So that's very interesting. That means the actual real gas volume is about 49% of the ideal gas volume, which is a huge difference, right? This was part B. Now, by following the same procedure, calculate the volume of the tank now using the Amagat's law, right? In Amagat's law, again, we know that we have to consider the real gas behavior. I mean, Pm Vm is equal to Zm Nm Ru Tm. I mean, not using the ideal gas behavior, use the real gas behavior. So again, we need to calculate the value of the compressibility factor. Now, here comes the difference between the K's rule and the Amagat's law. According to the K's rule, I mean, you can calculate the value of the Zm by considering the substance as a pseudo pure substance. But now the procedure for calculating the Zm using the Amagat's law is a slightly different. I mean, in this case, I mean, again, Vm is equal to Zm times this factor. This is the volume of the ideal gas, right? This is the volume of the ideal gas. So basically, we need to calculate this one. So the procedure for calculating Zm is different than the K's rule. How the ZM will be calculated? ZM will be calculated. ZM is equal to sum of the product of Yi Zi. I mean Yi mean Y nitrogen, Z nitrogen plus Y carbon dioxide, Z carbon dioxide. So they, basically, as you can carefully see, this procedure says that instead of calculating the Zm from the critical pressure of the mixture or critical temperature of the mixture, you have to individually calculate Z nitrogen separately, Z carbon dioxide separately, right? And then you have to put this value and then you can get the value of the Zm. This is a slightly different procedure than the K's rule. Now, how to calculate this separately? Zn, I mean, let's say first for the nitrogen, it says that calculate the reduced temperature for the nitrogen, reduced pressure for the nitrogen. Reduced temperature for the nitrogen mean the given temperature divided by critical temperature of the nitrogen. So that's the reduced temperature for the nitrogen. Similarly, given pressure divided by critical pressure of the nitrogen. So that's the I mean the reduced pressure for this. From this one, now you can calculate the value of the Z nitrogen from the same figure A15B. Since in a mixture, I mean Avogadro's law is based on the assumption that the individual pressure and individual temperature, they are the same as the PM and TM, and whatever is the mixture pressure and the mixture temperature, they are the same as the individual temperature and pressure. So that's why Tm is same as the individual pressure, so Pm is same as individual pressure. So in this way we can calculate the compressibility factor for the nitrogen value as well. Similarly, I mean for carbon dioxide we have to calculate Z CO2 separately. Now for the CO2, I mean the reduced temperature for the CO2 is equal to the given temperature divided by critical temperature of CO2. Similarly, reduced pressure is equal to the given pressure divided by the critical pressure of CO2. So if we know the reduced temperature and reduced pressure, and then we can read the value of the ZCO2, which is equal to 0.30. And we already know the mole fraction of nitrogen and mole fraction of CO2 that we calculated in part B. Now, if we put this value, I mean 0.25 times the Z nitrogen plus Y CO2, Z CO2, and then we have 0.48. Right? In part B, we calculated the value of the Zm was 0.49 instead of 0.48. So that's a slightly different, right? About 1% different. So again, if we put the value Zm times the volume of the ideal gas, now Zm we have is 0.48 times the volume of the ideal gas, which is 1.33. So now we have 0.638 cubic meter by using the Avogadro's law. So if we compare, I mean Avogadro's law with the K's rule, I mean the value of the procedure for calculating the Zm is only different, and the value come out to be that was 0.48, whereas the value of the Zm based on the K's rule that was 0.49. So about 1% different. So that means K's rule and Avogadro's law, they are very close to each other, only 1% different. But if we compare with the ideal gas equation, the huge difference both for the Avogadro's law as well as K's rule. I mean, in K's rule, it was about 49% of the ideal gas, whereas the Avogadro's law is about 48%, about 48% of the ideal volume. Right. So up to now, we have calculated the pressure, volume, temperature of a mixture of gases using both the ideal gas as well as real gas behavior. Next objective is how can we calculate the properties of the gas mixture both using the ideal gas as well as real gases behavior. Now, the properties of the gas mixture, properties mean the internal energy, enthalpy, entropy, specific heat, Cp value, Cv value. I mean for the mixture. Up till now you know how to calculate the enthalpy of the individual gas, how to calculate the change in enthalpy of the individual gas. What about if the gases are in mixture And again, mixture can be of ideal gas mixture and it can be of real gas mixture. So how to calculate those properties? That's the objective. Now let's start with the extensive properties of the gas mixture. You know, already know what are the extensive property and what are the intensive property. Extensive property mean which are dependent on the mass and size, and intensive property which are independent of the size and the mass. Now let's see first of all the extensive property. For example, if you want to calculate the internal energy of the mixture, let's say in mixture you have many components, then what will be the internal energy of the mixture? Internal energy of the mixture is the sum of the internal energy of all the component. Let's say if there are three component, then u1 plus u2 plus u3, right? So that's simply the summation of the internal energy of all the component. But usually, I mean, the data available in the property table, that data is normally in kilojoule per kg. I mean, the data available is in specific internal energy. Then to calculate the extensive internal energy, then you have to multiply the mass of each component with the internal energy. I mean, sum of m1 u1 plus m2 u2 plus m3 u3. Sometimes the properties are available instead of kilo per kg. The properties are in terms of per kilomole. Then you have to multiply with the number of moles, right? So same apply for the enthalpy. I mean, enthalpy of the mixture is equal to sum of enthalpy of all the components. So similarly for the, I mean the this one, I mean this specific enthalpy multiplied by the mass, or if the enthalpy is available in kilojoule per kilomole, then you have to multiply with the kilomole. Similarly, same apply for the uh, entropy of the mixture. I mean, entropy of the mixture is equal to the sum of the entropy of all the individual component, right? So this is how we can calculate the extensive properties of a gas mixture. Now, consider a small example. I mean, let's say we have a gas A, which is of 2 kilomole, and gas B, which is of 6 kilomole, and the internal energy of the gas A is, let's say, 1000 kilojoule, and of B is 1800 kilojoules. So what will be the internal energy of the mixture? Simply the summation. I mean, using this equation. Simply you add up. So there are two components, so you add up that. So you will get 2800 kilojoule. Now what about the how to calculate the change in properties of the gas mixture? This was simply, I mean, without the change, just for the, I mean, let's say state one. So let's say if the gas changes from state one to state two, there will be change in the property. So how to calculate the change in internal energy of the mixture? Again, that will be the sum of the change in the component I plus change in I mean, let's say if there are three components, then delta U1, delta U2, delta U3. So the change in each component you have to add up. Let's say that there is a change in internal energy of the nitrogen, there is a change in internal energy of the CO2, there is a change in internal energy of another gas. Then you have to add up the changes in individual gases. Then you sum up, that will give you the change in internal energy of the mixture. So again, if the properties are, I mean, the delta U available is in property table is in terms of the specific properties, then you have to multiply the mass of, or if it is available in the mole per kilomole, then you have to per kilomole, then you have to multiply with the per kilomole of that gas. So same apply for the enthalpy as well as for entropy. I mean, to get the change in the entropy of the mixture, that will be the sum of the changes of all the component, right? So this is how you can calculate the properties of a gas mixture. Now, there are, in addition to the extensive property, there are intensive properties as well. So how to calculate that for the mixture? Let's say how to calculate UM for the mixture. So you have to add up the product of the mass fraction. I mean, let's say in the mixture there could be three components. Then you have to first calculate the mass fraction of all the components. Then you have to multiply with the internal energy. So let's say mf1 u1 plus mf2 u2 plus mf3 u3. So you have to add up that depend on the number of components. So I'm talking about, let's say k value is 3, so three components. So from 1 to 3 mean, let's say three component. So you have to mf1 u1 plus mf2 u2 plus mf3 u3. So this is how Based on the intensive property, you can calculate the value of the um for the mixture, which has three components. And if the properties, these properties instead of per kilo kg, if they are that available per kilomole, then you have to multiply instead of mass fraction, you have to multiply with the mole fraction. So same apply for the enthalpy and same apply for the entropy. They are the same value. For the enthalpy of the mixture is equal to the sum of the product of MFI and HI. And if that's available in kilomole, then you have to multiply with the mole fraction instead of the mass fraction. And we have other properties like the CV and CP. Again, that's a CV of the mixture is equal to the sum of the product of MFI and CVI, depend on the number of components. Let's say if there are two components, then MF1 CV1 plus MF2 CV2. So you have to add up that. Sometimes the CV is available in terms of kilojoule per kg per Kelvin. If it is per kg, then you have to multiply with the mass fraction. If it is available in terms of per kilomole, then you have to multiply with the mole fraction, right? So same apply for the Cp. That's at this is at constant volume, whereas Cp is at constant pressure. So same apply for the Cp as compared with the Cv, right? So the properties which are available per unit mass, you have to multiply with the mass fraction, and which is available in per mole, you have to multiply with the mole fraction. Now these relations that are discussed for the extensive property and intensive property, they are exact for the ideal gas mixture. However, they are approximate for the real gas mixture. So that means we can blindly apply for the ideal gases. They will give you very accurate result. But for the real gas mixture, they will give you approximate result, right? Now consider this example. Let's say we have two gases, gas A which has 2 kilomole, gas B which has 3 kilomole, and the specific internal energy of the gas A is a 500 kilojoule per kg, and the specific internal energy of the gas B is a 600 kilojoule per kilomole. So what will be the specific internal energy of the mixture? So which formula will be used for this one? Yeah, we have to use this formula. This formula. Right? First of all, you have to calculate the mole fraction of each gas. How can we get total mole is 5? So Ya will be 2 divided by 5 and Yb will be 3 divided by 5. So you have to, mole fraction, and Ua and Ub are already given. So if you put this value in this equation, you will get 560 kilojoule per kilomole, right? Now, how to calculate the property for the gas mixture? We already know that for the ideal gas behavior, right? We know the enthalpy, internal energy, CV and CP. They are a function of temperature only. So you have to just add up. Let's say HM will be equal to HI, H1 plus H2 plus H3. And H1, H2, H3 we can calculate it from the property table. Similarly, the internal energy we can calculate from the property table. So you have to just add up the individual internal energy, and then you can get the internal energy of the mixture. Now for the change, however, there is a slightly different for the entropy. We know that entropy, change in entropy, we already know the formula for any two stages. Let's say state 2 and state 1. Let's say the state is changed from 1 to 2, then SI, this is the standard entropy which is available from the property table. This is for state 2 and this is for state 1. Please focus that this pressure will be the partial pressure of that component. This is the component, this come, let's say delta S1, let's say. So instead of I we can put 1 1. First component, can be nitrogen, it can be CO2, right? So you have to use the partial pressure of that gas instead of the the gas total mixture pressure. Is this the only difference, that here the pressure will be used as the partial pressure, right? That we can also simplify this one. You study in thermodynamics 1 that the standard change in standard entropy is a CPILN T2 by T1. So this is component I. So every time you have to put I, and this is partial pressure. Please note that this is partial pressure, not the mixer pressure. Right? The properties are available like uh, per kilomole. Then instead of Cp, there is a bar. So this represent that the properties are in terms of per kilomole instead of per kg. Here is per kg. If there is a bar, that means properties are available per kilomole. And how to get the, I mean this one, how to get the partial pressure? This was discussed in previous class that the partial pressure can be calculated by multiply with the mole fraction of gas component with the mixer pressure. I mean mixer pressure multiply with the mole fraction of that component will give you the partial pressure of that component. Similarly, let's say this is for state 2. So similarly for state 1 we can calculate Pi1 means state 1 is equal to mole fraction of 1 at state 1 times Pm at state 1. So this is how we can calculate the partial pressure at state 2 and partial pressure at state 1. Whereas there is no problem in calculating the HM, UM, CVM or CPM for the mixture of an ideal gas. This is just because those properties are just the summation, right? As I mean, based on the previous slide formula, it depends on whether we have to calculate the change in delta U or HM for the mixture. So accordingly, you will apply the formula, right? What about the real gas mixture? Now, for the real gas mixture, I mean, we can use that general relation that were derived in previous chapter. If you remember Maxwell relation, one of the Gibbs equation, if you remember, delta H is equal to TdS plus VdP. Right? Here, if we put M mean for the mixture, right? That's the TdS relation for a gas mixture, right? And we just modify that. Let's say that differential D is outside, and instead of HM we can put sum of MFI HI. Similarly here SM we can put sum of MFI SI. Similarly for the VM we can put sum of MFI VI, right? And let's say this is common, this sum of MFI is outside, and inside will be delta HI minus TM delta SI minus VD is equal to 0. So this is again equal to 0. So DH is equal to TMDS plus VDPM. So that means we can apply that generalized equation for the that were derived in previous chapter. I mean these were the generalized relations for the real gas, and those relation can also be applied for the real gas mixture. Now it, and how we'll calculate the Tm and Pm? How we calculate the I mean pressure for the mixture over volume for the mixture? We can apply, I mean, for the real gases, we can apply either the Avogadro's law or we can apply the K's rule, right? For example, when we'll apply the Avogadro's law, when we need the, I mean, VM, I mean, volume for the mixture, and when we'll apply the Dalton's law, when we need PM, right? When we need the pressure for the mixture, it depends. Just for, let's say, if we want to calculate the volume for the mixer using Avogadro's law, then we have to calculate the ZM, right? Compressibility factor for the mixer. And how we calculate ZM? We just calculated an example in previous slides. We calculated how we calculate the ZM for the volume of the mixer. Similarly, let's say sometimes it says use the K's rule. In K's rule, the procedure it assumes that the mixture is a pseudo pure substance, and the procedure for calculating the value of ZM is different. So based on that, we'll calculate, let's say VM or PM, and then we'll put that value here, let's say TM or PM. So accordingly, we'll calculate the value of the TH. So hopefully in next coming classes, we'll solve couple of numerical problem and you will understand how we can calculate the properties of the mixture using ideal gas as well as using real gas mixture. For example, in this example, let's say we have two real gases, let's say real gas A and real gas B, and they are available at the same temperature and same pressure, but they have different volume. Let's say one A gas A has 0.4 cubic meter and gas B has 0.6 cubic meter. Now, how to calculate the volume of the real gas mixture? Now, we have to use one of the law, either Avogadro's law or the K's rule. right? We already solved this the similar numerical problem in this class. If you see the previous slide, how we calculated the volume of the tank using different technique, using three different technique: ideal gas equation, K's rule, and Avogadro's law. So this is how we can put the value and we can calculate the change in properties. So that's the end of this lecture. If you have any question, you can ask me. In next class, we'll try to solve the related numerical problem so that you can understand the physical meaning of this theory. See you in the next class.